All right, well, welcome to our recording for the lecture for section 6.3. So we've spent the last two sections introducing the concept of power series, and we've really learned quite a bit about how to construct power series, how to use known power series to construct more power series. In this section, we're going to kind of consolidate that knowledge into some formulas that make it just a little bit more efficient to construct power series. We're going to introduce some terminology that's pretty important in the study of power series. Some terminology that really just takes the form of a couple of names from the time of Isaac Newton in the late 1600s. A couple of his contemporaries that were doing a lot of work on calculus at the same time. And in particular, building off of his work were Colin Maclaurin and Brooke Taylor, both living in what we would now call the United Kingdom, although it was not united at that time. Maclaurin was in Scotland and Taylor was in England with Newton. But they were, relatively speaking, in close proximity to each other and building off of each other's work. Their names are pretty closely associated with power series, so we're going to learn exactly how those names are used and how that becomes terminology for us. And then we're going to address something that has kind of been lurking in the discussion, and that is if we use a power series as a proxy for a function. A power series has infinitely many terms. We can't really use all of them most of the time unless we can figure out how to sum that infinite series. But if we knew how to do that, we probably would have a formula for the function. So if we don't have an algebraic formula for the function, and we're going to use power series to get an approximation with a finite number of terms, how good's the approximation and how do we know? So those are the questions we're going to be addressing in this section. Okay, so here's our outline for section 6.3. In previous sections, we've derived power series centered at 0 for two functions, y equals e to the x and y equals cosine of x. Both of these we derived from scratch. Okay, we didn't use our knowledge of geometric series, we didn't use our knowledge of other power series. In both cases, we built power series for these functions from scratch by simply assuming that there was a power series centered at 0, and then we just took derivatives over and over again to help us figure out what the coefficients of the terms would look like. Okay, so in this section we're going to generalize that into a formula so that we don't necessarily have to think through that every time. So here's what we're going to do. Okay, we're going to say generically, let's say we've got some function y equals f of x, and let's say that it has a power series centered at, we'll start with centered at x equals 0. I left out an x there. Okay, and if it's centered at x equals 0, then the power series would look like a constant plus a constant times x plus another constant times x to the 2 and another constant times x to the 3, and so on. Okay, now the idea is that those constants change from term to term, so they're a function of n, where n is just tracking what term we're in. Okay, we have figured them out for some specific functions, but now let's do it generically so we can get a formula for the nth constant, okay, as a function of n. Okay, so a formula for c sub n in terms of n. All right. Alright, so here we are with our generic function f, and we're assuming that it's possible to build a power series for f that's centered at 0. Okay, since it's centered at 0, we don't have anything subtracted from the x's. We can generalize this later and say if it's possible to build one that's centered at some other number, then that number would show up as something subtracted from x in each term. But that doesn't actually turn out to have really any impact on C0, C1, C2, C3, the coefficients, okay, or at least not really no impact on how we go about getting them, okay. All right, so first things first, notice that if I plug 0 in for x, everything disappears on this side except the c0. So by necessity, f of 0 is c0. Okay, let me make that look a little nicer. There we go. So that's pretty straightforward. The first term in the power series, the constant term, okay, is just whatever f of 0 is. Now, if I had a number subtracted from x, if my series was centered at some other number, then that number is what I would have to plug into f to get all the other terms to disappear. So say, just for the sake of argument, say the series was centered at 5, then I'd have to plug in 5 to wipe out all these other terms. So in that case, I would conclude that f of 5 was c sub 0. But basically, f of whatever x value we're centered at is the first constant. Now, if I take the derivative of f, this is pretty much what we did for e to the x and cosine x. We're just being more generic now. Okay, if I take the first derivative of f, that term goes away. This term becomes just the c1. That term becomes, I got to bring that 2 down, so I get 2c2x and then 3c3x squared. What I'm doing on the right hand side here really should look exactly like what I was doing previously for e to the x and cosine x. I mean, the only real difference is I just haven't specified what the function is. But now I'm again going to plug in the x value that I'm centering this series at. So I'll plug in 0, and that wipes out all of these terms, and it just leaves the c1. So the first coefficient was f of 0. The second coefficient is f prime of 0. Let's take another derivative. Okay, f double prime of x. Alright, so when I take the second derivative, the c1 goes away. This term becomes just a constant. In this term, I've got to bring that 2 down. So now I have a 6c3x, and I've got a 12c4x squared, and so on. Okay. And so again, I'm going to plug in the x value that the series is centered at. So f double prime of 0 wipes out everything but the first term, equals 2c2. So now I have to divide by 2 and say, alright, f double prime of 0 over 2 equals c2. Okay, let's differentiate a couple more times. So if I take my third derivative, alright, now that's going to wipe out the first term. This term becomes a constant. 6c3 plus 24c4x, and there'd be some more terms, but I'm not too worried about those. I'm going to stop here pretty soon. Alright, so if I plug 0 into the third derivative, that wipes out everything but the first term. So f triple prime of 0 is 6c3. So if I want to get c3, okay, my fourth coefficient, because it's on the degree 3 term, the first term was constant. If I want to get my fourth coefficient, I need to take the third derivative and divide by 6. And of course that 6, we could really think of that as being a 3 factorial. Okay, because it was first there was a 1 there, then we brought down a 2, then we brought down a 3. So it's 1 times 2 times 3. Okay, let's just do one more derivative. Fourth derivative of x. So now the 6c3 goes away, and I get a 24c4. Okay, and then there'd be some other terms, okay, starting with something times x and then something times x squared. But if I take my fourth derivative and I plug 0 in, everything's going to disappear except that very first term. Which means that if I want to get c4, I need to take the fourth derivative, plug in whatever x value I'm centering the series on, and then divide by 24 But 24, of course, is really 4 factorial. Because how did we get that 24? Well, originally there was a 1 with the C4, then we brought down a 4, then later we brought down a 3, okay, and then later we brought down a 2. Okay, so it's 4 times 3 times 2 times 1. So apparently, the formula for the coefficients involves really just taking the appropriate derivative of the right order, plugging in the x value that we're centering the series on, and then dividing by the associated factorial. So if I want to generalize, I could say that c sub n is the nth derivative, okay, the nth derivative of my function, evaluated at 0 or whatever number we're centering the series at, and then divided by n factorial. And that even works if we go back up to the earlier terms, because 2 is the same thing as 2 factorial, and then 1 factorial is 1 and 0 factorial is 0, so we could think of these as being divided by 1 factorial and 0 factorial. So the formula holds, and that brings us to the first theorem of the book. So let's have a look at the first theorem here in section 6.3. Okay. I called it a theorem, but you could also call it just a definition. Okay, we derived it. Okay, this is a formula for constructing a power series for a given function centered at a given value. Okay, so let's say, rather than saying 0, let's say we're going to center this at x equals a, where a is some number. Okay, then in that case, I would have a constant term, and then I would have an x minus a term, and an x minus a squared term, and so on, up through an x minus a to the n term, and on to infinity. And the coefficients, well, this is what we just derived. The coefficient of each term would be given by the nth derivative of that term with a plugged in, divided by the nth factorial. Okay. And here the 0th derivative would be understood to be the function itself. So the function itself is used to get that first constant term. Now, generally speaking, when we construct power series using this formula, we refer to it as a Taylor series. Okay, that's just a reference to the mathematician Brooke Taylor, who was a contemporary of Isaac Newton. Okay, it's also convention that if we're talking about a Taylor series that's centered at 0, which is often the case, we often center them at 0, then in that case we call it a Maclaurin series. Okay, Taylor and Maclaurin were some of the first people to publish extensively on power series, so their names kind of got tied up with these things. All right, let's talk about how to use this formula to construct a power series for a function from scratch. So we just talked about that. Let's go to this example at the bottom of the first page of the outline. Construct a Maclaurin series for y equals hyperbolic sine. Okay. Now, as we just mentioned, Maclaurin means centered at 0. A Maclaurin series is a power series centered at x equals 0. Okay, so we're constructing a Maclaurin series. All right. So here's our function, f of x equals hyperbolic sine of x. Okay, as a little side note, we'll want to refer to this later. Okay, the definition of hyperbolic sine is that it's 1/2 e to the x minus 1/2 e to the minus x. And hyperbolic cosine is almost the same thing. It just has a plus between the terms rather than a minus. Now, of course, we could build this either by using the fact that we've previously built Maclaurin series, we didn't call them that, but power series centered at 0 for e to the x. And in fact, we've even built them for hyperbolic cosine, so we could just integrate or differentiate either one, because both the antiderivative and the derivative of hyperbolic cosine is hyperbolic sine. So we could, let's say, differentiate the series that we built for hyperbolic cosine last time to get a series for hyperbolic sine. But I want to use this to show you how to use this formula to build a series from scratch. This is kind of a nice function to do it with because its derivatives are pretty simple. Okay, the first derivative of hyperbolic sine is hyperbolic cosine. And then the second derivative is the derivative of hyperbolic cosine, which is back to hyperbolic sine. Okay, and then the third derivative goes back to hyperbolic cosine, and the fourth derivative goes back to hyperbolic sine. And let's do one more derivative here. Now there's no hard and fast rule here, but if you're going to use the Taylor formula to construct a power series, it's usually a good idea to start by computing maybe the first 4 or 5 derivatives. You want to compute enough derivatives that hopefully you'll be able to see a pattern with what happens when you start plugging in the x value that you're centering the series on. Okay, so f of x is hyperbolic sine of x, so f of 0 would be, well, let me see, if I plug 0 in, I would have e to the 0 is 1. I'd have 1/2 minus 1/2. Oh, that's 0. Okay. And then f prime of 0. So I'm plugging 0 into my first derivative, which is hyperbolic cosine. And if I plug 0 into hyperbolic cosine, I'm going to get 1/2 plus 1/2. Alright, that's 1. Okay. This one is going to be pretty easy to pick up the pattern on these derivatives. So the second derivative at 0 is 0. The third derivative at 0 is going to be back to 1. The fourth derivative evaluated at 0 is 0. And then the fifth derivative evaluated at 0 back to 1. Okay. So if I want to write out my power series, I can say that hyperbolic sine. Alright, so remember my formula. Alright, so when I follow my formula, the first term should be f of 0, and then the second term should be f prime of 0 times just x to the 1. Okay, now if I was centered at anything other than 0, I'd have to write x minus something. Okay, and then for the next term, now I've got to start worrying about the factorials because they won't just be 1s anymore. It's the second derivative at 0 over 2 factorial times x squared, and then the third derivative at 0 over 3 factorial times x cubed. Okay, and then the fourth derivative at 0 over 4 factorial times x to the 4, and then plus, let me write at least one more here, plus the fifth derivative at 0 over 5 factorial times x to the 5, and we'll say dot dot dot. Okay, now looking back at the work we did up here, I can see that, you know what, that's a 0, that's a 0, that's a 0. It looks like we're only going to have odd degree terms. Now that's a 1, that's a 1, that's a 1. So I can say that hyperbolic sine looks like it's x plus 1 over 3 factorial x to the 3 plus 1 over 5 factorial x to the 5. And then I'm assuming that Well, let me see. If I did my sixth derivative, that would be a 0 again, so there wouldn't be a degree 6 term. The degree 7 term would be 1 over 7 factorial x to the 7, and then we'd have a 1 over 9 factorial x to the 9, and so on. Okay, and that looks like something we could pretty easily put into sigma notation. We could let n go from 0 to infinity and say, alright, that's going to be 1 over, we want just odds, so we'll do 2n plus 1 factorial x to the 2n plus 1. Now I said on the outline that we should compare that to the power series centered at 0 that we built last time for sine. Okay, so I'll just say for comparison, previously we said that the power series for regular sine, now remember this one also only had the odd terms, okay, but that one was an alternating series, so it was almost the same formula. The only difference was that we had this negative 1 to the n, negative 1 to the n over the 2n plus 1 factorial x to the 2n plus 1. Okay, so that it alternated between positive and negative. But apart from that, the power series centered at 0, or Maclaurin series for hyperbolic sine, same as the one for regular sine. Nice little parallel there. And it makes it a little bit easier to remember. Alright, let's go back to our outline. Alright, so we built the entire Maclaurin series for sine of x, or actually for hyperbolic sine of x. But let's see what we mean by Taylor and Maclaurin polynomials. So the book gives a definition for this here on page 563. Okay, I've got to scroll down a little bit. We were on 562. Okay, so the nth Taylor polynomial. So remember, a series is an infinite polynomial, but here we're talking about a finite polynomial. The nth Taylor polynomial for f at a is basically just the same thing as the Taylor series, except we're going to stop after just n terms. So this will be a finite polynomial. And you could think of that finite polynomial as being a partial sum that should be an approximation for the entire Taylor series. Now the reason we talk about Taylor polynomials is because if I want to actually use a Taylor series to get values of a function, I really need to take just a finite number of terms, so therefore a Taylor polynomial, and use that for my approximation. Okay. Now again, if we happen to be talking about something that's centered at 0, we might use the term Maclaurin rather than Taylor. Okay, that part of the terminology is consistent. So let's find the 5th degree Maclaurin polynomial for y equals hyperbolic sine of x, and use it to approximate hyperbolic sine of 1. Alright. So here was the entire series. If I've already constructed the series, it's not too hard to come up with a polynomial that just uses some of the terms from that series. We were to find the 5th degree Maclaurin polynomial for hyperbolic sine, so that means we're going to take all the terms up to the 5th degree. Okay. Now the notation, since we're using a finite polynomial rather than an infinite series, is we'll call it P for polynomial. We'll use a subscript to remind ourselves what degree we're going to take. And then we're basically just going to write these first 3 terms. So x plus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th. Now I actually have something that I could do calculations with. Okay, if I plug a value in for x in this, it should give me an approximation for hyperbolic sine. Now, how good the approximation is, we'll have to think about that in a minute. Okay, but it should be hopefully not too far off. Okay, let's do that approximation. So hyperbolic sine of 1 would be approximately equal to this fifth Maclaurin polynomial with 1 plugged in. So if I plug 1 in, that's not too bad. I'm just going to have 1 plus 1 over 3 factorial plus 1 over 5 factorial. Let's put that into the calculator and see what we get. So 1 plus 1 divided by 3 factorial is 6, plus 1 divided by, alright, if you don't remember what 5 factorial is, you can put in the 5, hit the probability key, and select the factorial symbol. Okay, so according to this, my answer is 1.175. You know what? Let's compute the exact value of hyperbolic sine just for comparison. So to compute the exact value, I'm going to have to use this formula up here. Okay, now if you happen to have a calculator that has a hyperbolic sine button, you can make use of that, but otherwise, we can always go back to this. So 1/2 e to the 1 minus 1/2 e to the negative 1 is, well, you know what, it's not too far off. It's 1.175 and then some change. So this was the approximate value, but then the true value, or at least the true value to as many decimal places as my calculator is showing, is 1.175201194. So you know, actually that's good. That was accurate out to 3 decimal places. This is one of the really nice things about these Maclaurin and Taylor polynomials. Okay, because the coefficients have factorials in the denominator, the terms shrink in size pretty quickly, which means they tend to converge pretty quickly. We usually don't need very many terms to get pretty good approximations. Okay, now this turned out well for us, but if we didn't have the exact value of hyperbolic sine, we wouldn't really know how good it was. And of course, if you do have the exact value of hyperbolic sine, then you don't really need to do an approximation. So it begs the question, in situations where we don't have the exact value, which is exactly when we would do an approximation, how do we know how good our approximation is? Well, we've got a theorem just for that. Okay, it's called Taylor's theorem with remainder. Okay, I'm back here on the outline. Okay, but Taylor's theorem with remainder is on page 568 of the book. So let's have a look at that. Scroll down, scroll down, scroll down, scroll down. Here we go, Taylor's theorem with remainder. Okay, so we're talking about a situation where we've computed the nth Taylor polynomial, and we're going to use that to approximate our function f of x. Okay, our nth Taylor polynomial is basically just a partial sum of an infinite series. So if I take the difference between f of x, the true value, and the partial sum Pn of x, then my error is just all the remaining terms that I'm leaving off. Okay, that's what the book is calling big R. Okay, but here they give us a formula for big R. Okay, they tell us that remainder would be actually pretty close to just being the first term we left off, even though it really represents all the infinitely many terms we left off. We can get that remainder basically just by taking the n plus 1 term. In fact, the only thing that makes this expression here not the n plus 1 term is this c here. Okay, if that was an a, because remember we always take whatever number we're centering the series on and plug it into the derivative. If that was an a, then this would be the n plus 1 term. Okay, but I wouldn't really expect that to be right because that would be leaving off all those other terms. But what Taylor's theorem is saying is that there's some x value somewhere between x and a. That's what we're calling c here. There's some x value that if we plug that into the n plus 1 derivative and then compute the n plus 1 term, then that would be exactly what the error is. Now the catch is, there's no easy way to know exactly what that x value was. I mean, if there was, we could get the exact error, add it to our approximation, and get the exact answer. Okay? Yeah, we usually can't do that. But what we could do is we could figure out what is the maximum of the absolute value of the n plus 1 derivative, okay, on the interval between x and a. Okay? If we can figure out that maximum, then we can substitute that maximum into our numerator, and then we can actually do a calculation for what would be an upper bound for our error. Okay, so basically we have to compute the n plus 1 derivative, figure out its maximum value between the value the series is centered at and the value where we want to do our approximation, okay, a and x. We call that maximum big M, and then we take big M and we divide that by the n plus 1 factorial and multiply it by x minus a. So again, x is the number we were trying to get our approximation at, a is the number we're centered at. Multiply that by x minus a, absolute value, to the n plus 1. I know that sounds like a mouthful, but if you've already pretty much got down the formula for the terms, this isn't too much of an adjustment. Let's see what that looks like for our function. So this was an approximation based on the fifth Maclaurin polynomial. Okay, so in order to get an upper bound for the error without having to know the exact value there, we're going to have to compute the sixth derivative. Well, I had stopped at the fifth one, but fortunately the sixth one, pretty easy to compute. If the fifth derivative was hyperbolic cosine, then the sixth derivative is back to hyperbolic sine. So we'll go ahead and write that on the next piece of paper here. The sixth derivative of f is hyperbolic sine. Now, the x value where we're trying to do our approximation is 1, so that's what Taylor's theorem was referring to as the x. The a value, the value where we centered our series, is 0. Okay, so we want to find m, which is the maximum of this thing here, this sixth derivative. So it's the maximum of hyperbolic sine. Okay, really the maximum of its absolute value on the interval from 0 to 1. Okay, if we can fill in that blank, the rest of it will just be plug and chug. But this is the part that takes a little bit of thinking. So remember, hyperbolic sine looks like this. It looks like 1/2 e to the x minus 1/2 e to the negative x. If I want to find the maximum of a function, and that's what I need to do here, we learned in Calc 1 that to find the maximum of a function, you usually want to start by computing its derivative. So the derivative of hyperbolic sine is, of course, hyperbolic cosine, which is almost the same thing, just with a plus sign in the middle. Oops, left out a half there. Now, here's the key thing about this derivative. Okay, 1/2 e to the x, always positive. 1/2 e to the negative x, also always positive. Okay, and since they're both have positive terms in front of both have positive signs in front of them, I can say this is always positive. Okay, so the derivative of hyperbolic sine is always positive. I couldn't be quite so sure that hyperbolic sine itself is always positive, okay, since one term is negative, although I think it probably is, since it looks like that would be the smaller term, okay, at least for positive x values. But definitely the derivative of hyperbolic sine is always positive, so hyperbolic sine itself is always increasing. Now this is something you're going to have to pay attention to as you work problems. Some functions you're going to deal with are going to be always increasing. Some will always be decreasing. And some might have a max that's in the middle of the interval. Okay, if it's always increasing, then you know you're going to find the max at the right endpoint. If it's always decreasing, you know you'll find the max at the left endpoint. And if it's not always one or the other, then you're going to have to find values where the derivative is equal to 0 and look for a local max or a local min. Okay, but anyway, since hyperbolic sine is always increasing, we can say, therefore, its max value, you know what, there's no apostrophe in its when we're using it as a possessive. Its max value is, so let's say its max value on the interval from 0 to 1 is at x equals 1. Okay, so m equals hyperbolic sine of 1. Now, I gotta tell you, if you're thinking about this very hard at all, you should probably at this point be thinking, wait, our goal is to get an approximation for hyperbolic sine of 1, but it looks like we need to know what hyperbolic sine of 1 is in order to put a bound on our error, and that's kind of a problem. I mean, if we need to know the exact value of the answer in order to see how good our approximation is, then we're kind of screwed, because that's the thing we're looking for. Okay, but a lot of times in a situation like this, you can simplify by making a change. That gives us something a little bit bigger than m that we do know the value for. So here's the idea. Remember, hyperbolic sine of x is 1/2 e to the x minus 1/2 e to the minus x. So hyperbolic sine of 1 would be 1/2 e minus 1/2 e to the negative 1. Now, I know that e is like 2.7-ish. So if I replace that e with a 3, that makes this bigger. So this would be less than 1/2 times 3. Now the advantage there is I know the value of 3, it's 3. Okay. Now I got to think about this. Would it also have the same effect over here? Well, if I replace e with something bigger than e, then that's going to make the denominator bigger, which would make the fraction smaller. But that would mean we're subtracting something smaller. So yes, replacing this e with 3 also makes the entire quantity bigger. So I'm going to go ahead and say 1/2 3 minus 1/2 3 to the negative 1. And if I simplify that a little bit, that's 3 halves minus 1/6. So that would be 9/6 minus 1/6 is 8/6, or 4/3. So even though I didn't come up with an exact value on m, I can say that m is less than 4/3. And now I can go back and use my formula. So let me remind you what that formula looks like. Here's the formula. Once we come up with m, we take m, we divide it by n plus 1 factorial. So remember, in this case, n was 5 because our approximation was based on a 5th degree polynomial. So we're going to be dividing m by 6 factorial. And we're also going to be multiplying by the absolute value of x minus a to the 6th. Okay. Got it? Got it. Well, I got it. Okay. So, maybe I'm overusing that word. So, our error is less than or equal to 4/3 divided by 6 factorial times the absolute value of x is 1, a is 0, to the 6th. So that's all just 1. Okay, that's subtraction there. So I think I'm back at a point where I can start plugging stuff into my calculator again. So really I just need to plug this in. So 4/3 divided by 6 factorial. Hopefully that's not a real big number. 4 divided by 3 divided by 6 factorial. Well, let me see. That's 0.0018. So my error should be less than 1/1000th. And when I go back and look at that comparison, yes, it did turn out to be the case that my error was, let me see, if this had been a 6 here, that would have been off by 1/1000th. So yeah, we were definitely off by less than 1/1000th. Okay, pretty good. Pretty good. Now, let's look back at that outline again. So we gave our upper bound. Okay. But now, here's the next question. We know our error is less than 1/1000th, but usually there's a specified error that we need to get under, and we need to figure out how many terms do I need to make sure I'm under that error. 5 terms is enough to make sure the error is less than, it was 0.0018, so really less than 2/1000ths. Okay, but how many terms would I need to be sure that my error is less than, say, 0.000005? If it's less than, look at that, after the decimal place, that's 5 zeros and then a 5. So if it's less than that, it basically means that the approximation is good to 5 decimal places. So maybe that's what we want. There's a certain number of decimal places that we want to be correct. Okay, so how big would n need to be for that? Okay, well, let's have a look at this. So remember, our derivatives were flipping between hyperbolic cosine and hyperbolic sine. And every time the derivative hit hyperbolic sine, since we were centered at 0 and hyperbolic sine of 0 is 0, we basically lost that whole term out of the series. So there's no even degree terms. Because of that, I know that really my Maclaurin polynomials for hyperbolic sine need to be odd. So let's just kind of say that up front. Okay, we don't know how big n needs to be, but let's say n is odd. If n is odd, any odd order derivative is hyperbolic cosine. That leaves me to a coefficient of 1. Okay, so there we'll actually have a term. Okay, so let n be any odd number. Any odd positive number, I guess. Okay, then our nth derivative of x. So remember, f of x is the function we're approximating, hyperbolic sine, but our nth derivative is going to be hyperbolic cosine of x. Okay, and our n plus 1 derivative is going to be hyperbolic sine. Okay, so we can say that m, which is going to be the max of the absolute value of our n plus 1 derivative on the interval, this case from 0 to 1, by the same reasoning we went through before, m has got to be less than 4/3. Okay, so the error, give myself a little more room here, the error has got to be less than 4/3 divided by n plus 1 factorial, okay, times the absolute value of 1 minus 0 to the n plus 1. Okay, now if this number here were anything other than 1, I would have to worry about this part of it, but since that's a 1, this part of it is always going to be a 1 for this problem. Okay, I want that to be less than 0.000, and I lost count there, 0.0000, 5 zeros and a 5. Now, because of the factorial, I pretty much have to do this by guessing and checking, by just plugging in numbers for n. Okay, but the good news is, because we have a factorial in the denominator, this fraction should shrink pretty quickly. So let's just start at it. So 4/3. Let me see if I can get that to focus just a little better. Good enough, I guess. Divided by, so we did have 6 factorial, so that was 5 plus 1 factorial. Okay, now that did not give us a number less than 0.000005. So let's try going a bigger n value. Now remember, we said n has got to be odd, so let's go up to 7. Okay. Oh, that shrank quick. 0.00003. Alright, we're not quite down to being this low yet, but we're getting there pretty fast. Let's change that 7 to a 9. Alright, that number, 0.0000, yeah, there's 6 zeros there. That's definitely less than this number. So 9 is big enough. Okay. So n needs to be at least 9. Okay, and that means that if I take my 9th Taylor polynomial, so my 9th Taylor polynomial, Maclaurin really since it's centered at 0, my 9th Maclaurin polynomial, remember that would look like x minus 1 over 3 factorial x cubed, actually it was plus 1 over 5 factorial x to the 5, plus 1 over 7 factorial x to the 7, and then 1 over 9 factorial x to the 9. Now if I take my 9th degree Maclaurin polynomial and I plug 1 into that, I should get an approximation for hyperbolic sine that's good to at least 5 decimal places. So if I plug in my 1 here, I would get 1 plus 1 over 3 factorial plus 1 over 5 factorial plus 1 over 7 factorial plus 1 over 9 factorial. Let's plug that into our calculator. So clear that out. Yeah, there we go. 1 plus 1 divided by 3 factorial is 6, plus 1 divided by 5 factorial is 120, plus 1 divided by, I don't remember 7 factorial, so I'll let the calculator compute that one, plus 1 divided by 9 factorial. Okay, that gives me 1.17520. Let me go ahead and write that down. 175201168. Now, if we've done everything correctly, that should match the true value of hyperbolic sine at 1 to at least 5 decimal places. Now, we had that a moment ago. Here was that number. I'll write that down again here. It was 1.175201194. Well, there's my first 5 decimal places. Yeah, it definitely matches that far. In fact, it goes a little further. Catches one more even. So, we did it. Okay, we did it. All right. Well, you know what? This is pretty much the concepts I wanted to go over in this section. But I want to do another example where we center the series somewhere else, just to make sure that it's clear what that looks like. So let's have a look back at the outline. Alright, last example. So we're nearing the end of page 2, and that'll be it for this outline. Let's find the fourth Taylor polynomial for the function y equals the square root of x at x equals 4. So notice we're not centering it at 0 this time. Okay, so I'm not going to call it a Maclaurin polynomial, I'm going to call it a Taylor polynomial. Alright, so here's the function that we're building a Taylor polynomial for. Okay, now we were specifically told in the instructions to build a 4th degree Taylor polynomial. So I know specifically that I need to go down to the 4th derivative. So I'm going to begin by computing the first 4 derivatives of this function. So first derivative, bring down a 1/2. Power decreases by 1. A half minus 1 is negative a half. Second derivative, bring down a negative 1/2, I get negative 1/4, x to the minus 3/2. Alright, I need 2 more. Third derivative, I'm going to bring down a minus 3/2, and I'll get 3/8, x to the minus 5/2. Alright, I need 1 more. So a fourth derivative, I will bring down that minus 5/2. I'll get minus 15 over 16, x to the minus 7/2. Now, we're centering this Taylor polynomial at x equals 4, so 4 is the number I've got to plug in for the x's. Now 4 to the 1/2 is square root of 4, that's 2. Okay, so f of 4 is 2. Okay, so that's going to be the first term of my polynomial. Okay, I can start building my polynomial down here as I work on this. So this is the 4th degree Taylor polynomial, and the first term is just going to be a 2. Okay, now for the second derivative, I have 1/2 times, it's going to be 4, I'm sorry, I said second derivative, this is the first derivative. It's going to be 4 to the negative 1/2, which means the 2 is in the denominator. So it's a half times a half, basically. So f prime of 4 is going to be 1/4. So that's going to be the coefficient on my next term. So the first term is always a constant, but then it's going to be a constant times x minus the number that we're centering the series around. Okay, now let's go to the second derivative, f double prime of 4. So I've got a negative 1/4, and I'm going to have 4 to the negative 3 halves. Now, when I compute 4 to the 3 halves, the half gives me a square root of 4, which is 2, but then that 2 gets cubed by the 3, so that becomes an 8. But the negative means that 8 is in the denominator, so I get negative 1 over 32. So for the next term of this is my Taylor polynomial of degree 4 for f of x equals square root of x. My coefficient is going to be negative 1 over 32. But remember, I need to divide by a factorial. I didn't bother for the first two terms because 0 factorial and 1 factorial are both 1. But now I better divide by a factorial. 2 factorial will be 2. And I need to multiply by x minus 4 to the 2. Okay, 2 more to go. Let's compute the third derivative with 4 plugged in. Alright, so when I plug 4 in for x, the 2 in the denominator of the power makes that a 2. The square root of 4 is 2. 2 to the 5th power is 32. But that 32 is going to be in the denominator because the power is negative. 32 times 8. 32 times 8, that'd be 256. That's in the denominator. So it'd be 3 over 256. Alright, so for my next term, it's going to be 3 over 256 divided by 3 factorial times x minus 4 to the 3. And I've got one more term in this polynomial. So plus. Alright, so when I do my fourth derivative, evaluated at 4, square root of 4 is 2, 2 to the 7th is 128, but that's in the denominator. So that's negative 15 over 16 times 128. I don't think I can do that in my head. 16 times 128 is 2048. Alright, so maybe I need to give a little more room here. Plus negative 15 divided by 2048, and that's got to be divided by a 4 factorial and multiplied by x minus 4 to the 4. Alright, now that is my fourth degree Taylor polynomial. I think I am going to go ahead and simplify these fractions, but that wouldn't be an absolute essential. Okay, it'll make it look a little nicer. Alright, so let's go ahead and grab that. So that'll be 2 plus 1/4 times x minus 4 minus 1 divided by 32 divided by 2 is 1 over 64, x minus 4 squared. And then here, 3 divided by 3 factorial would leave a 2. So that's going to be 1 over 512, x minus 4 to the 3. And then minus, let me see. Negative 15 over 2048 over 4 factorial. It's the best way to go about doing that. So negative 15 is negative 3 times 5. Now that 2048, remember that was a 16 times a 128. And then I've got a 4 factorial down there. So that's 4 times 3 times 2 times 1. So I guess I can cross out some 3's. That's going to give me negative 5 over. And then I need to multiply this stuff back together. So 16 times 128 times 4 times 2. 16,384. So, yeah, that's a thing. Minus 5 over 16,384 times x minus 4 to the fourth. All right, all of that was part A. We constructed the polynomial. Let me see if I can clean that up a little bit. That's supposed to be an 884. There we go. Now it only looks slightly bad. All right, let's do the next part. So we found our fourth degree. Let's throw in the word degree. Fourth degree Taylor polynomial for y equals square root of x centered at x equal 4. Use the result of part A to approximate square root of 6. All right. So part B, the square root of 6 should be approximately P4 of 6. So now I got to plug 6 in here. Every time I plug 6 in, I'm going to get a 2. Okay. Well, I think I'm ready to just start plugging that into my calculator. I'm not sure I even really feel like writing it all. Alright, so that would be 2 plus, let's bring that up a little bit better. There we go, 2 plus 1 divided by 4. And then 6 minus 4 is times 2. Minus 1 divided by 64 times 2 squared. Plus 1 divided by 512 times 2 cubed. Okay. And then minus 5 divided by 16,384 times 2 to the fourth. Okay, so 2.448, yeah, let's just write all that out there. 2.448 2188. Now that's an approximation. Now I know just from thinking about it that the square root of 6 would be more than the square root of 4, which is 2, and less than the square root of 9, which is 3. So yeah, it seems feasible. Hopefully it's accurate at least for a few decimal places. Now part C, let's look at our outline again. Part C is to find an upper bound for the error of that approximation there in part B. So for that, I'm going to need to compute another derivative. I used the fourth degree Taylor polynomial, so I'm going to need the fifth order derivative. All right. Well, let me see. Where was that fourth derivative? The fourth derivative was there. So I guess to get the fifth derivative, I'll have to bring down a negative 7 halves. So let me see. 7 times 15 is 105. 16 times 2 is 32. Alright, so the fifth derivative of our function is 105 over 32 times x to the, now it was negative 7 halves, so now it'll be negative 9 halves. Okay. We need to find the max value of that. So m would be the max value of the absolute value of our fifth derivative. Now in this case, remember a, the value we centered at was 4, and x, the value we were actually trying to get an approximation for, was 6. So we're looking at the interval from 4 to 6. Now, this function is a continuously decreasing function. How do I know? I know it's decreasing. Let's actually write this down. I know it's decreasing because if I take the derivative of this function, it's going to be negative, because I'm going to bring down a negative. So here's my fifth derivative. You know what, here's another way you could know without having to argue based on derivatives. I'll just bring that down there. 32x to the 9 halves. Okay, x to the 9 halves is increasing, so this function, it has a continuously increasing denominator. It's continuously decreasing. But you could also compute the derivative of this function and show that it's always negative. And that would also allow you to argue that that function is always increasing. So this function is always decreasing. So its max value on the interval from 4 to 6, well, since it's always decreasing, my max value's got to be at the beginning. Okay, will be at x equals 4. Now, I got to be a little bit careful. If this function were alternating between positive and negative on this interval, my max value wouldn't necessarily be at the beginning, because we're taking a max of the absolute value. But this function is always positive, so I don't have to worry about that. Okay, so let's plug 4 in. So I want to evaluate my fifth derivative at 4. So that'll be 105 over 32 times 4 to the 9 halves. Okay, I think at this point in time I want to just let my calculator do the thinking on that. So 105 divided by 32. Now I want to put that whole denominator in parentheses. So 32 times 4 raised to the 9 divided by 2. I've got to put that power in its own little set of parentheses. So close the power, close the denominator, and that is 0.006400. Yeah, let me just write that down. 0.06408,691. Haha, there we go. That is our value. Okay. Now remember to get our error is less than m over n plus 1 factorial times the absolute value of x minus a to the n plus 1. Now here, n was 4, x was 6, and a was 4. So that means we've got to do m over 5 factorial times 6 minus 4 to the 5. So I've got to take that number, divide it by 5 factorial, and multiply it by 2 to the 5. Fortunately, I still have that number in there. So I'm going to say, let's divide u by 5 factorial, but also let's multiply by 2 to the 5, and that gives me 0.001708. Okay. So my error is less than or equal to 0.001708,984. Okay. So in particular, that tells me that I've got at least 2 decimal places accurate in my answer. Let's have a look at that. Okay, here was my answer down here. This was my approximation of the square root of 6. We should be good for at least 2 decimal places. Let's get the let's get a more accurate version of the square root of 6 from our calculator here and just do a quick comparison. Yep, 2.449. Yeah, we had at least 2 decimal places right. All right. Well, that's everything I wanted to go over for section 6.3. So here's the textbook homework problems, 126 and 134. Okay, let me know if you have any questions about those or about the problems in My Open Math. And at this point, we're wrapping up, so let me again just encourage you. If you need any help, reach out to me. I hope you're all doing well. I hope you've all stayed healthy, and I hope you continue to stay healthy. Be safe, my friends. Bye.